All right. Thank you so much to the organizers for this wonderful workshop. I very much enjoyed my time in Madrid so far. I'm happy to be telling you something that's maybe a little bit different from many of the other talks. As I know many of the people in the room here are not really in this field at all, the talk that I prepare is much more kind of an overview, broad talk. But I will give kind of a couple of examples of things that I've been doing at not a super deep level, but just to kind of show you what are some of the interesting things you might think about doing with these sort of new tools that we have in quantum information science in application to high energy theory and cosmology. So the work that I'll display quickly is in collaboration with these various folks who are most of who have been at Syracuse University at one point or another, with the exception of Royce, who's actually outside physics and helped us make some pretty pictures that I'll show you later. Okay, so, well, so I'll start with a few slides of motivation. So quantum computing is this new tool in our arsenal of tools for studying field theories in regimes that are, as I'll explain the reasons why, difficult to access with current classical hardware. So some things you might imagine doing with these tools are things like real-time quantum dynamics, which maybe you might imagine someday Pythia has built into it a little quantum part of its algorithm that actually directly time evolves QCD states forward to give you jet evolution. Additionally, there are particular kinds of interesting field theories that maybe are field theories beyond the standard model, but that we have a difficulty in understanding what the predictions will be for those in the strongly coupled regime because of what we call the lattice sign problem that I'll give some details on. So theories with chiral fermions, for example, are problematic. Additionally, strongly coupled theories at finite density are difficult to study using classical hardware, where again, the lattice sign problem crops up, and we're unable to, for example, figure out what QCD looks like at very large densities, at very large baryon density. What's I think interesting right now is that this field is sort of in its infancy, with sort of a long time period where we might start to really make progress on the things that we're most interested in on the time scale of 10 to 30 years. So it sort of parallels development like in the LHC, when you're in the 1990s, you're looking forward to this big awesome experiment. What are the things we can do with that experiment? We're trying to figure out those sort of things. What are the applications for this that maybe people haven't thought of yet? It's in the sort of white paper stage. And additionally, there's feedback and crosstalk between theorists and experimentalists. Maybe we have some great idea that would not be possible given kind of the current trajectory of the quantum information science and computing field, but maybe that helps develop for experiment in the direction that would best help us. And additionally, there are tens of gigadollars flowing into this field, and so that means that there's potential funding for postdocs and exciting careers for people who have some background in this field. And I'll go again to this. Okay, so just what are some of the reasons why we want to actually do quantum simulation of things rather than classical simulation? The main one is that Hilbert space is very big. So, for example, if I was interested in studying some sort of simplest field theory like the 1 + 1D Ising model, which is just a string of qubits coupled to each other via a nearest neighbor interaction. This is an interesting system in that there's rich dynamics. There are sort of quasi-particles on either side of a quantum critical point as you adjust the strength of this transverse magnetic field term. And there's the special point when you tune this term to critical value, at which you develop long-range correlations in this system, right? And you only see those long-range correlations if you're able to simulate at large enough volumes. But if I have n sites, the size of the Hilbert space grows like 2 to the n. And so the matrices exponentially grow, and if you try to do this on Mathematica, you can maybe get to n equals 16 or something like that before the thing just craps out, and you have to give up. And so, of course, we know a lot about the Ising model, but this is just one an example of a field theory. We might think of other types of interesting models with different sorts of interactions, maybe about which we know a little bit less than the Ising model. We know a lot about this theoretically already. We don't actually need to simulate the Ising model, but there are other interesting field theories that we can do potentially. And so, additionally, there is the lattice sign problem that obstructs our ability to take certain field theories and put them on the lattice and studying them using standard Monte Carlo. And the problem is one of complex weights in the partition function, where if I were to it's sort of the original assigned problem is the fact that if I want to do a quantum mechanical path integral, there's an I in the exponential, and this is a solvable sign problem. You Wick rotate and lattice field theorists, rather than studying this, study an analog four-dimensional Euclidean space statistical physics system from which you get the correlation functions that then correspond to the correlation functions for the quantum mechanical system. And so this fixes this sort of first sign problem. So now let's see how you can get additional sign problems even after you perform this trick. So for fermions, you can't directly sum over fermions in these path integrals, because there's just no type Grassmann, right? You can't implement Grassmannians in C++. So what you do is you integrate out the fermions. So you start off with your path integral here, you Wick rotate and get this analog statistical physics problem. You integrate out the fermions, which if it's quadratic just gives you this Pfaffian, or the square root of the fermion determinant. However, this thing is typically going to be complex valued, unless you happen to be in a vector-like theory where the eigenvalues are come in complex conjugate pairs, and this ends up being real in that particular case. So there's no problem doing QCD because QCD is a vector-like theory. But if you're interested in some technicolor-like theory that has a chiral structure, then you would have trouble here. Or just any other strongly coupled theory, forget technicolor, just any strongly coupled theory that maybe is part of your favorite dark matter sector or something like this, you'll run into issues trying to simulate it. And it also happens at finite baryon density, or just finite density in general. And the reason is the following. When you introduce a finite chemical potential in the statistical partition function, you introduce it by adding a term to the exponential that is mu times the charge. But we all remember that the charge has an I in it. And so when you, again, you end up with complex weights. So when you try to sum over this, the Monte Carlo just oscillates all around the complex plane, and you get very poor convergence. Okay.
Sorry, isn't it true that even in QCD beyond one generation, you have this problem? I mean, there are people talking about even sign problem with when they try to simulate the car.
Yeah. So this is true for QCD as well. So this is why you can't go out using lattice very far on the mu in the mu direction.
Without chemical potential, you're saying that the three-generation QCD doesn't suffer from.
Correct. It does not suffer from a sign problem. Okay. And
if theta angle is equal to 0.
What's that?
If theta angle is equal to 0.
Okay. And yes. Right. Topological terms are another thing that introduces the sign problem. Very good. Very good.
But theta would be even a problem for one generation. I think that if you include phases with more than one generation, you cannot get rid of them, and then you can get also.
Right. So whenever you have a topological term that is another thing that you would like to simulate, that is also going to run into the sign problem. But QCD, we know the theta angle is minuscule, if not exactly zero. Very good. Okay, and so this is, I just wanted to say, and this is true for fermions as well, and there's a quick check of whether you have a sign problem, which is this gamma 5 hermiticity. And so if you have the chemical potential, then it does not satisfy this gamma 5 hermiticity, and so you have a sign problem there as well. And so this will be there for QCD at finite density, and so as long as the theta term is zero, we can do perfectly fine studying QCD on the lattice along this axis, or using perturbative techniques, very, very small chemical potential. So you can't get very far away from this line here, but there's a lot of exciting stuff along this axis that we don't have direct access to via lattice simulation. Okay. And why should we care? Well, there are these astrophysical objects that put QCD at very high densities, and we are now getting data about what the interiors of these stars look like from LIGO, which when you have a neutron-star collision, the chirp signal has imprinted upon it information concerning sort of the squishiness of the stars, which has to do with the equation of state of the material that makes up the star. And in order to get the equation of state, we need to go out at high chemical potential. And so we only have sort of ad hoc models for writing down what's going on here with not very good control over theoretical uncertainties. So if we were able to do lattice inside here, we would get access to the equation of state, and there, once we have the equation of state, we might be able to separate, for example, your favorite new physics model that maybe alters the effective equation of state inside the neutron star and disambiguate it from the standard model prediction. So the issue is we don't have a standard model prediction, and without a standard model prediction, we can't use these things to learn about, maybe your favorite model of dark energy, which some of us here have played with. Maybe these neutron stars tell us something about why our cosmological constant is so small, and among various other different models. Okay, so step in quantum computing at a very rough level. Quantum computing handles the eyes for you automatically, and of course it internally handles the large to the ends. And there's different kinds of implementations of these systems. There are gate-based machines where what you do is you map your field theory of interest, your system of interest, onto a bunch of qubits. And you come up with a quantum operation that you want to perform, which maybe corresponds to the Hamiltonian for your system of interest. You take the unitary that you get from the time evolution using that Hamiltonian, and you break it up into quantum logic gates that only act on 1 or 2 qubits at a time. And once you perform this decomposition, you can just run a circuit like this forward that is effectively simulating your field theory of interest. There are also what you might call analog quantum simulators, where you sort of design a system of, say, atoms that mimics in some way your system of interest. And so you sort of design this beforehand, and you go ahead and say to your experimentalist friend, okay, here, build this thing. It'll simulate QCD at finite density, and they go ahead and build it, and you'll work it forward, okay, and study that system as a proxy for the full QCD.
So can I ask, what are the qubits here?
Sorry, in which?
How? So if you
Here?
Yes.
Yeah, so each one of these lines corresponds to one of your qubits.
But
and
what is the qubit? So you discretize how you implement it?
So it depends. Maybe it's a superconducting qubit, which is basically just a little RLC circuit, and this is an oscillator. And maybe you develop a little nonlinearity so that only the 2 lowest states are active in the system. or maybe it's just a two-level atom, where again you put the atom in such a configuration that it's limited to only one or two states, a lowest state and excited state. There's this could be any system. You don't know.
I wonder how you go from your field theory to qubits.
Okay, I'll say a couple words about that. Yeah,
because for the Ising model, I understand it. But
sure. Yeah.
I don't know how to do it.
Yeah, I mean, you have to work model by model, and figure out what is the way to break it down. That's the quick answer. So what do things look like right now? Like, what are we currently able to work with? We're in what's called the NISQ era, the noisy intermediate scale quantum era. And there are chips right now that have on the order of 100 to 150 qubits, but these are very noisy. You can't effectively use these entire 100 qubits and expect that you can entangle one end of your chain with the other end of your chain within the time period that the system starts to fall apart and decohere. And so realistically, you can entangle a handful of these qubits nearby, and so you can't really use the whole thing. The idea is right now they're just building them as fast as they can to develop a pipeline for designing these things, over which time they'll increase quality control and coherence and things like this. That's my rough picture of what's happening. So, for example, at IBM, they have machines that are available, and through right now collaboration with a BNL scientist, we have access to something like a 30-qubit machine that we've been able to experiment with, but we are seeing this kind of problem where you can't really use the entire system. But this is going to improve over time. Okay, these systems don't have any error correction, and so you can't expect that the Hamiltonian that you're trying to implement is going to be, exactly, what the system ends up doing, from input to output. I'll say a couple of words at the end. There are some interesting developments in creating machines that are kind of hybrid between the analog quantum simulation and the more gate-based description that I had, where you program in the geometry that you want for your qubits to have in their layout, and that geometry dictates how the guys are interacting with each other. And so you can kind of say, you don't need to go to your experimentalists and tell them to build a whole new thing. You just say, this is the geometry I want. They steer all the atoms around for you and put them in the configuration that is best for your model of interest. And these are kind of cool. And I'll say some words about them at the end. And so the thing you should get from the last slide is that we're super far away from putting QCD on a quantum chip. But most of us are familiar with the long game. We know how to work with delayed gratification. And so right now we're working and asking what can we in principle achieve using these things, and how does this field need to evolve in order to meet our goals, as I said before. So the rest of my talk, I'll talk a little bit about how you take your system of interest and break it up into gates that you might put on a machine, and then I'll talk a little bit about work that I've been doing, which has to do with open quantum systems, and also sort of discretizing anti-de Sitter space and looking at sort of a lattice version of ADS-CFT. Trying to go away from what you would call the large N limit, where bulk physics starts to become strongly coupled. So these are things you might imagine doing with these systems. There's many other things that people are working on, but I'll just highlight these two ideas.
So can I ask something before the So I mean, there are many places where no chemical potential, no phases, just the QCD is blocking us from doing precision tests, right? Like hadronic physics, matrix element, form factors. If you can improve them, it will be amazing. So we're saying there's no chance. It's not where quantum computing helps.
I suspect not. I'm not enough of an expert on the actual classical lattice things that are maybe there's hope for doing the chiral extrapolation a bit better. Again, I'm not sure. I say this kind of off the cuff. Maybe there are improvements that you could make here. I would guess that those are super far away before you have machines that are large enough on this side that you would actually be able to tackle that problem. But yeah, I don't know. Okay, so how do we approximate e to the minus IHT? The algorithm is called the Suzuki-Trotter algorithm. And the idea is you just do a, you build up a large time evolution by breaking it down into a bunch of itty bitty time steps. And when you do this in a field theory, this is particularly nice because field theories are local. And so that means when I write down my Hamiltonian, it's only a sum over terms that are acting on one single space-time point and nearest neighbor type interactions, okay? And so here's a picture of that. So this is kind of like a lattice array of qubits. You can maybe imagine that this is the way that your quantum machine is actually distributed, where the qubits lie on the chip. And you can maybe say, maybe I need 9 qubits per site to accurately represent whatever physics is going on. So say if it's a scalar field theory, this gives you an occupation number of up to 2 to the 9, right? Your scalar field can go up to that value. That's the number of states that you sort of truncate to in your simple harmonic oscillator. And so here's one site, and then I have some sort of nearest neighbor interactions that interact these qubits with these qubits, okay? And you just sum up over all of these, and here's your two-dimensional field theory that's been discretized for you. Okay, so now when you discretize time into small steps, you have your big forward time step breaks up into a bunch of little time steps, and you can approximate the evolution to order delta t as these little things that only involve, and they factorize because of Baker, Campbell, Hausdorff, as long as the delta t is small, the other terms are suppressed compared to this guy here. And so your e to the IHT, in the limit that delta t goes to 0, is well approximated by only the little unitaries of what's going on locally, plus what's interacting, each site with the next site over, okay? And then it's your business then to do the, at this point, much more relatively simple task of breaking up this small unitary into some sort of quantum logic gate or operations that you would perform on one of these programmable quantum simulators. So for example, your quantum Ising model, if I only have 4 sites, looks something like this, where these are phase rotations about z. These are phase rotations about x. These are entangling gates that are like your nearest neighbor interactions. These are what are called controlled knot gates. And this thing implements the nearest neighbor interaction, and these implement the physics site by site. Okay, and then in order to do a large time step, you just do the DCL coda. If you know music, you repeat the number of times that you want to. And if you have a noisy computer, then you only repeat the number of times before you lose coherence completely, and this becomes meaningless. Okay. So you start off with some initial state density matrix and go forward. Okay, why open quantum systems? And I'll relate this back to this idea of a finite density. If I have an open quantum system, then the idea is that you have some system of interest. It's coupled to some sort of environment, and we're used to doing effective field theory, right? We want to ignore the complicated stuff or the stuff that we're not directly interested in, and only focus in on the physics that's relevant for us. So here's the part I care about. Here is the rest. And there are different ways you might sort of partition this picture. Maybe the part that I care about are the QCD fields. The rest is the bath of baryons. Maybe this is my observable universe, and the rest is whatever is outside the horizon that I even in principle have no access to. Or maybe I have stuff that actually hits my detector versus some very weakly interacting stuff that I have no chance of actually seeing. And so the idea is we want to trace out over the stuff that we don't have access to and understand what the effective evolution will be of the part that I care about. And in general, this evolution is not going to be unitary, right? Because there is some sort of interaction between my system of interest and this environment and any interesting implementation of this. And so if I have some initial state density matrix, it's not going to evolve unitarily. There's going to be something that happens to that density matrix that depends, A, on what's going on inside the system, and B, what's going on in the environment and the coupling between the two. So it will depend on all of these things. Now, the presumption is that this whole thing is evolving unitarily, and we can use that evolution in order to figure out what this effective non-unitary evolution will be, right? So now we're most familiar with integrating out sort of ultraviolet degrees of freedom, and in this case, of course, the evolution of your system after you trace out the ultraviolet modes remains completely unitary as long as you only probe the theory at energies less than whatever your cutoff is, right? If you try to go outside this, it's going to have a non-unitary evolution. So generally it's the case that tracing out this environment yields non-unitary evolution, and pure states are typically going to evolve into mixed states. So if I start in a pure state here, this will end up being a mixed state in general, which represents the entanglement with the environment. So then what is this E? What is this operation? And you can, I won't focus on the details here, but the basic idea is when I trace out over the basis states for whatever my environment is, and use the full evolution of the system plus environment to do the unitary evolution part, when I trace out over the environment, I'm left with a set of operators EI acting on my only my system of interest. And where I know what these EIs are, if I know what the full evolution is, and I know what the basis of states is for the environment. So I can calculate these EIs if I know the full picture, okay? And this is called the Kraus operator decomposition. And there's a remnant of the overall unitarity of the initial system plus environment that appears in a requirement on these E's, which is that if you sum over the EI dagger, you end up getting the identity. And this just says that probability must be conserved. No matter what happens to rho of S, its trace must be equal to 1, okay? And so really, you should think of this as what we mean when we say a system is evolving unitarily, right? Because we never have access to everything in a system, right? There's like infrared stuff that we can't measure, even in principle, right? And so you imagine tracing over this. This will be the effective evolution of your system when you get rid of the stuff that when you trace over the stuff that you have no direct access to. So just an example that folks are hopefully familiar with here. So we can think about the KK bar system where there are oscillations between the kaon and the anti-kaon, and then kaons of course also decay, right? So if I were to focus only on a system of kaons, this is an open quantum system because the kaons have some decay products, and I can imagine tracing over those decay products to get an effective evolution of only my KK bar system. So now, what are the outcomes that I can observe if I have a KK bar system only? Either I find a kaon, I find an anti-kaon, or I find no kaons at all, right? So there's a 3-state system that is my system of interest in this case. And I have sort of an effective Hamiltonian governing that system of kaons, anti-kaons, and the vacuum state, where this G parameterizes the oscillation, gamma parameterizes the decay matrix, and now if I have some initial state density matrix describing how I start the system off, then it evolves into a sort of evolution of the upper left block of this guy using this non-Hermitian Hamiltonian, but because there's decays of the kaons, the trace of just this part is becoming less than 1, so there needs to be a compensating piece at the bottom here that maintains the trace of the overall thing. So now when you calculate the Kraus operators, there's one Kraus operator that implements this effective non-Hermitian Hamiltonian, and then you have two other Kraus operators that serve to populate this sort of block down here. So one does this, and the two others populate this in accordance and to maintain the overall trace equal to 1. Okay, and so this is nice because I've taken a very complicated physics problem of kaons decaying into complicated final states. The dimension of that final state space is infinite, right? The decay products can go every which way, in different angles, blah blah blah. But now we've boiled the effective description down to just these three simple operators, E0, E1, and E2. And so now you can ask the question, how do I go the other way? So given an effective theory description, how do I go back and figure out what the environment is? And of course you can't, right? This process is not invertible. There's a general theorem, though, that says for any evolution of any system of interest, the maximum number of E's that I need to describe the evolution of that system is D squared if my system of interest is of dimension D, right? So this means that to do any physics on this system, I only need a polynomial overhead in additional things that implement these E's to describe the physics of the system, okay? So if you want to simulate some arbitrary open system, you can represent the environment without additional huge resource requirements. So what is this didn't quite work. So what does our kaon circuit look like? I have 2 qubits to describe the kk bar, and the vacuum state. That's 4 states, but I just have a padded 0 at the end of the array, okay? Here's my environment. So this is 2 what we would call ancillary qubits. I have some big overall unitary that I figure out how to implement that non-Hermitian Hamiltonian and create that Kraus operator decomposition for the evolution of this after I trace out over those ancillaries. So it's up to me to design what that U is that implements the physics that I want. The states of these ancillaries over here tell us which of those 3 E's actually happened, whether the kaons oscillated or they decayed, right? And so now let's do a non-trivial thing. So this is the quick example. Maybe I might think about taking the Ising model and now study it in the field in the regime of complex couplings. So this is a little bit like taking QCD at finite chemical potential. It's like a very, very baby version of this. So I have the quantum Ising model, but now I've added this dissipative term. So this is my effective Hamiltonian in analogy with the kaon Hamiltonian. And I find some way to map this effective Hamiltonian onto a set of qubits that represent my system and as many ancillaries as I need to mock up an environment that implements this dissipation, okay? And so now what is the physics of the Ising model with this crazy dissipative term? This is well studied in the case of the StatMech version of this system. When you crank up this dissipative term, this Hamiltonian is not Hermitian, yes? And so the eigenvectors are no longer orthogonal to each other. And in fact, what you can get is a special point where the eigenvectors sort of merge together and you actually just lose an eigenvector. So the Hamiltonian becomes only diagonalizable up to Jordan block form. And in this particular model, the 2 lowest states, energy states in the theory, move towards each other along the real axis, and at this special point where the Hamiltonian is only diagonalizable up to Jordan block form, the guys split off into the complex plane as I go further. And so there's a funny critical point in the space of complex couplings that corresponds to what is known as the Li-Yang edge singularity as I take the volume of this system to be large. If I have finite volume, I still get this sort of exceptional point where the eigenvectors merge, and this is just the lines for various number of sites where that happens. So I get novel critical phenomena in the space of complex couplings, and you can see that as I take the number of sites large on the real axis, that hx equal to 1 is that critical value where the Ising model has its quantum critical point, okay? And so if you like, these sort of exceptional points are like they're related to the quantum critical point of the real space Ising model. Okay? And these are analogous to sort of a phase transition at finite density. And you can go ahead and you can design a circuit that has the right ancillaries to implement that dissipative term. And here's that circuit that does one time step. We can play in Mathematica and figure out, what the evolution of this system would look like, starting from some initial state and, evolving a long time, getting that final state. And there are things you can measure for the system, like the Rayleigh entropy of the final state, where there's a clear signature where the Rayleigh entropy is big on this side of the transition, and then just dives down on the other side, right? So there's a clear indicator of this, the phase transition in the space of complex couplings in a quantum simulation of this open Ising model. So this is just a classical calculation. This is done on Mathematica, not a quantum computer, but we can do it on one. So here is just a one-site Ising model, and the blue curve is the theoretical prediction. The red dots are what the quantum computer spits out. You see that it actually does fairly well. And the exceptional point is right here, where there's a sudden turnover in the way that the observables are behaving across that phase transition. And here is, okay, now we finally actually have an Ising model. It's only 2 sites, right? We can't do very big. And we're measuring something slightly different. It's this just the expectation value of sigma z. But again, you see sort of a clear difference in the behavior of the system on either side of this critical line. So you can actually see things that you would predict on the system, right? So we know what happens with the Ising model. The idea would now be to take some non-trivial model where we don't have theoretical predictions in the space of complex couplings. We can think of this as kind of like a benchmarking, right? Do we see what we expect to see? One thing that we'd love to do as sort of further benchmarking is figure out something associated with that critical point. Cardy predicted that the central charge of the CFT associated with being on that critical line is minus 22/5. It's negative. It's an open system. You don't expect the central charge to necessarily be positive. But we can, in principle, maybe extract that from observables. And so we're hoping to go a little bit further and see if this is possible. And again, like I said, study more interesting models. There are other sort of toy models of QCD at low dimension that you might study that we don't have theoretical predictions for yet at finite chemical potential. And so this would, again, be these baby steps towards getting to actual finite density QCD. Avi.
Cardy got that number?
Which number?
The minus 22.
What about the number?
How big is it?
I think he guessed it, and then there were a bunch of cross checks that were done after the fact. It was somebody we showed that this CFT was one of these what are called the minimal models. I don't know enough to really tell you exactly where that prediction comes from, except matching this system onto a set of CFTs that people knew about and studied. I think the guess was it's going to be a pretty simple thing with only a couple of operators in the CFT, and then it was a question of kind of mapping this system onto one of those. That's my quick thing. Okay. And so this is one thing that we've been kind of playing with, and this is again just to show you that there are some things that look a little bit like the studying models at finite chemical potential that maybe will help us down the line. So we want to build algorithms that in principle can be used down the line to do the thing that we really want to do, QCD at finite chemical potential. So another fun thing that I've been working on is sort of a discrete version of ADS CFT, where what we do is we tessellate the hyperbolic plane, and we're only working in Euclidean space here. This is not quantum dynamics. Right now, we're only studying the statistical physics problem, either in 2D or in 3D. And this is where this guy, Royce Nelson, was helpful to us. He's been building these lattices to make these really cool pictures of hyperbolic space on Wikipedia. And we didn't know how to generate the lattices to figure out on our computer where do the points go and how do we link them together. And so it was fun to collaborate with him to get the code for generating these lattices, not just as pictures, but as things that correspond to link variables or degrees of freedom that we might put on these sites. And the idea here is this is sort of the bulk in ADS CFT. This is the boundary, and there are ultraviolet scales in the picture, like the lattice spacing, and the the effective warping, which is like the curvature, which is determined when you say how I want to sort of glue these vertices together. Like, so hyperbolic space is, you can build it by sort of jamming triangles together. If I only jam together 6 at a vertex, I get flat space. And if I try to jam together more at a vertex, you get hyperbolic space. And if it's less, then you get a space with positive curvature. And there are infrared scales because I can't build a lattice forever on a computer, right? I can only go out so far in making pretty triangles. And so there's this boundary is of finite size, yes, and it's here it's a shape, it's a circle. But there's also sort of a depth, which is an IR scale, like how far I can go into the bulk before I don't have a geometry anymore. And so you might ask, what are the aspects of ADS CFT that sort of remain if we were to put fields on this? We studied the power law, the boundary-to-boundary correlators, for example, if we put a scalar field on this tessellated geometry. And indeed, the correlation functions are very nice power laws. And this is really just a consequence of the fact that geodesic distance is exponentially related to boundary distance. So if I have a gapped bulk, then the gap just appears as a power law when you write down the boundary-to-boundary correlator, which can leak through the bulk. There's a funny 1 minus cosine theta here, and that's because the circle breaks conformal symmetry, but it breaks it in a very predictable way. So when you plot it versus this, you expect to get back the power law again. And it matches precisely what you expect from ADS CFT. So we fit this curve to this formula, and it fits super nicely. So this is a first thing. We don't really care that much about free scalars in ADS. We might care about strongly coupled theories. So okay, we can do it in 3D also. It matches what you expect from ADS CFT. We can do strong dynamics in the bulk by building an Ising model in this geometry, putting essentially qubits on each site, and have a nearest neighbor interaction between them. And there's there's a temperature term that as I adjust the temperature, this 2D hyperbolic system goes through a phase transition just like the flat space one. So the bulk is gapped at high temperature, it's gapped at low temperature, but then there's some magic critical temperature where the bulk is gapless. Okay, and now we can again do the boundary-to-boundary correlators, and and again, just extract power laws. So you get back what you had for the free scalar field, but now for a theory which has all kinds of topological objects, right? Domain walls on one side of the critical point, and sort of flip spin quasi-particles on the other side of the critical point. So over here, the theory is pretty much kind of like a free theory. Over here, it's kind of like a free theory. And in this region, you're getting at the point where the bulk theory is strongly coupled. And so you expect there to be higher order endpoint correlation functions that are not just determined by the 2-point correlation function. So you have a really non-trivial kind of bulk theory that is away from what would correspond to the large N limit for the CFT. Again, it's not a gravity theory. This is rigid ADS, so it's not really small N ADS CFT, but it's baby steps towards that. You can imagine letting the geometry fluctuate, which would sort of correspond to a gravity theory in the bulk. And so what we're hoping to do is now do a quantum time evolution of this thing. So actually build a qubit array that it has the geometry of hyperbolic space, and then do time evolution of that thing forward. So a 2+1 dimensional theory, and study ADS CFT in a fully quantum mechanical context. And this is where those sort of programmable Rydberg arrays come in, which are really neat. You can build all kinds of things with these Rydberg atoms, which act as your qubits. So here's like a picture of the Eiffel Tower, if you can see it. Here's like sort of this hyperboloid structure. Right now, you can't do quantum computing on these 3D ones, but you can do it on sort of these 2D programmable arrays. So you stick in the picture that you want, the way that you want them to glue together. So I would put in my ADS tessellation, and then you just run the thing forward, and what you do is whenever you want to have a nearest neighbor interaction, you just steer the two atoms close to each other, and there's a van der Waals interaction that does the entangling for you and acts as a nearest neighbor coupling. Okay, so this is again just a quick example. If I wanted, I'll say my one cosmology thing. You might imagine now doing this thing dynamically with time, and so instead of this being the spatial geometry, I can imagine sort of adding qubits as a function of time. So this looks a little bit like inflation, yes? If time is in this direction, then I'm exponentially adding qubits to my interaction picture as I go outwards. So I can sort of study a version of inflation fully quantum mechanically in this kind of picture. And again, you could do it with these programmable arrays in principle. Okay, so I'll just wrap up here. So these were just a couple of examples of cool things you might imagine doing. The world is your oyster. Many things have not been done here yet. So I encourage folks, if you're so inclined, to figure out your kind of cool, wacky thing that you can study. But speaking practically, this really does hold promise for solving some long-standing problems in particle physics, and overcoming this sign problem is really one of the biggest promises that it holds out that are relevant for people in particle theory. As I've showed you, there's a couple of simple things that can already be done, and those simpler things are getting more complicated rapidly. The things that you can be doing are getting more complicated fast. There's lots of work to do. This is a big industry. I only talked about a couple of things, but there's a big industry in, for example, figuring out how to do Hamiltonian gauge theories and truncate them in a way that will actually reproduce the physics of a gauge theory on a real-time evolution system. It's a cool and fun playground, and hopefully one that will eventually hold out, will eventually really help us make progress. All right, thank you.
For this ADS CFT,
Yep.
So a key part of the ADS CFT is that you have gravity on it, right? Here it's impossible that you have gravity in the same.
Oh no, it's not impossible.
It's too massless emergent thing.
So
Cyber-Witten, not Cyber-Witten, Weimer-Witten tells you it's impossible. I mean, are relativistic, still too massless particle emerging from condensed matter systems. Say, I mean, I don't know how you can do it.
So if you actually wanted a spin 2 massless guy, so ADS CFT doesn't need to have the massless, spin 2 guy. Yeah, I can have, I take my UV boundary, I take this up to infinity. There's no normalizable graviton mode in this picture, and so what you would do in principle, and my colleague, one of my colleagues, Simon Catterall, is actually doing this. As what you have is a geometry that's dynamical, where the geometry is fluctuating, so this amounts to the connectivity of the lattice itself being dynamical. And then you just sum over the triangulations, which corresponds to the sum over geometry. So really what it amounts to is figuring a way to map the continuum gravitational path integral into a discrete path integral.
When I'm saying that, I would be surprised that you would recover something like GR, or something like what we normally understand on ADS.
Yeah, I wouldn't say that the goal is to reproduce GR. I would say that the goal is to study the ADS CFT correspondence at away from large N, where the geometry is strongly fluctuating rather than only weakly fluctuating.
Again, you're going to be in another universality class or whatever. You're not going to be in the same kind of.
Okay, you have to worry about this, but I don't think it's obvious that you're going to be in a different universality class. So that's a very important point, and the question is, how do you resolve whether you're in the right universality class? And that's an important issue. I mean, you could, in principle, you should be able to look at the weakly coupled limit, and if that reproduces things, then you might expect that as you go towards strong coupling, that you still remain in the right universality class. So there might be checks that you could do that would maybe help build your confidence in that kind of question.
In any case, it's an old question. How do you make spin 2 particle emergent? And there are some obstacles people know about. So maybe there is something.
Yeah, again, I'm not saying the goal is to get an emergent massless spin 2 guy. Yeah.
No. If you just have a CFT, you don't need to introduce gravity into the
But
CFT.
your simulation is, sorry, your
the massless spin 2 is your problem.
is it in 5D or is it 4D?
This is 2D.
2D.
Yeah.
It's not on the 2D side, and yet is it on the.
So I mean, the goal, of course, would be to do a higher dimensional thing. But this is just the baby thing.
Working on the CFT side or
No, yes.
Yeah, no, this is. I mean, the picture is obviously hyperbolic space.
Okay,
Space
then
of negative curvature.
it's true that you have to have a way, if you really, in the future you want to do it, you have to have a way to put a massless graviton in 5D. Okay? And discretization is problematic in any dimension. That's but probably that's not the.
If you have a true CFT, you do not have the massless spin 2 guy.
But you're working on the 5D side. You're working on the gravity.
If I take 5D and I take the boundary of ADS to infinity, there is no massless spin 2 field in the picture.
The 5-dimensional graviton is still dynamical, of course.
Oh.
I'm talking about the bulk of it.
5-dimensional gravity.
In the bulk.
Or for you, it would be 3-dimensional, whatever. But probably
maybe we continue after.
Okay. But I have a baby question about the Kaons system. Okay?
Sure.
Now, just to understand, so if you simulate the Kaons system in this way, so at some point your wave function, can populate the vacuum environment or ancillary.
Yeah,
but
eventually everything goes to the vacuum. Yeah.
Then it can also come back in the evolution. So when we think about the decay of the Kaon, we are thinking in a different way. Is this reproducing really?
So the Kaons don't come back. So I just have these guys and they decay into space. I'm not going to get the Kaons back, right?
Because the kinetic is of freedom.
So this corresponds to a specific class of open system that has the behavior that the information leaks, kind of one way, only into the environment. Yeah. So I have not given this. The Ising model that I talked about is not the most universal kind of openness that I might consider. It is indeed possible for some open systems where the information comes out, and then it returns again later in some non-trivial way. And that would have a different setup than the one that we have here.
So it is crucial for this to work is that you have a small number of states, because otherwise they will come back by doing this. So for example,
no, I mean it has to do with the setup of your environment.
Doesn't come back? It doesn't come back because there is a
because the stuff that it's made of is all the way over there. I'm not going to get it to come back together.
Number of degrees of freedom that you are tracing over. Okay? But when you do this, you only have a finite number. So is this a problem?
So again, it depends on the operation that you want to mock up. I said from the get-go that when my kaons decay, they're not going to come back because I know that their decay products, run away. Yes, that I'm not going to get back to the kaons, and so that's what dictates, the particular set of E's that we built here. The fact that there is this non-Hermitian Hamiltonian, effective Hamiltonian plus these E's that act as the things that decay. If I wanted to do something like this, I'd probably need a more rich set of E's. I probably couldn't do it with just 3 of them.
Yeah, but by the way, you need to be careful what you're saying about the count, because as we know, there is a type of CP validation which exactly measure the phase between gamma 1,2 and M12, namely that you can measure effectively the part of the Hamiltonian which, if you wish, related to the absorptive phase. So you go, decay, and you go back. There's actually a whole class of CP validating observer we can see. So I was hoping that maybe you will hint for that. You took another direction.
So again, you're sort of getting out what you put in here. If I were to put in that physics, then there would be, this would be a different set of operations that would incorporate, the physics. All I put in was the oscillation matrix and the decay matrix. So of course, that's what I get out on the other side, right? And so the thing that determines the operation that you want to implement here is, the full physics, which maybe in the case that you're interested in has more stuff here and more stuff here to account for whatever the operation that you're performing is. Yeah, maybe the purpose here is not to study chaos. It was just to give you an example.
Maybe this problem is a bit generic. For example, if you want to simulate something which interacts with a thermal bath, and you say the thermal bath is made of a small number of degrees of freedom, then you will have the problem that the thermal bath is not really a bath. Okay.
Sure.
So,
yeah, and so in that case, you need to be more careful about the way that you build this. So that would not be represented by this simple set of things. You need to do whatever the physics is that you're trying to model.
Okay. So you meant, so I have a more basic question about quantum simulations. So you have this advantage that you can basically handle the extremely large system, like this to the end. The quantum simulation does it for you, but you don't have then access to all the amplitudes and phases. You need to perform measurements and
yeah. So you need high luminosity. You need to do the experiment. Many times. Yes.
That the kind of questions you want to answer about particle theory can be answered with a limited amount of measurements, not having to do again an exponential amount of measurement, but then kind of spoils the whole idea of quantum simulation.
Right. So you need to be clever about the way you design the way you implement your system so that it's aligned along the observables that you're sort of most interested in, so that you don't need to perform so that like I have some huge density matrix associated with this Ising system here, or if I wanted to do more sites there. So the question is, what are the observables that I care about, right? And so maybe I'm just interested in sigma z, right? If that's the case, then I only need to average out sigma z over the whole system, right? And so in many cases you don't care about the detailed structure of your full to the n by to the n density matrix. You only care about some easier, more easily extractable observable. In addition, though, I have a field theory, right? And so the thing is translation invariant, and so there's a there's a symmetry built in at the density matrix that says I don't need to do everything at all the points. All right, and so you can see right away that to extract the stuff that you care about, you probably don't need to perform 2 to the n or more measurements to get out what you're interested in. So it's, again, you just have to be clever about the way you design the setup so that the information you're interested in is easily extractable.
Okay, so if there are no more questions, let's thank Jay again.